All right. Let me close this tab. All right, so today, welcome to Computer Graphics, everybody. So today we're gonna be going over ray tracing, global illumination, add some more, even more to the slides. The slide deck keeps growing bigger and bigger. So as we're learning about all the different techniques of doing ray tracing and global illumination. So we're looking at what used to be the slow one, which is ray tracing, and now it's kind of become the hot topic of the day. It used to be the hot topic in the 80s, and then and then it wasn't practical for real projects, and then now it has started to become practical for real projects again. So kind of the idea here is looking at ray tracing, looking at global illumination, and different variations on how you do those, and then talk a little bit more about real-time ray tracing. And today we're going to focus on kind of a new real-time technique called, well, it's, new. It's been out since like the early 2000s, but it's probably the de facto way of doing global illumination nowadays. And that's called irradiance volumes, pre-computed irradiance transfer. It's a kind of closely related to instant radiosity. It's another technique out there. We'll talk about instant radiosity another time. But the idea here, right, just to kind of review what is ray tracing. Let me just dim these, dim this just a little bit. Okay, so we have, backwards ray tracing is where we shoot rays from the camera into the scene, find out how they're going to reflect light in the environment. Forwards ray tracing, in contrast, is where you shoot rays from the light source and then you figure out where they're going to go. Okay, I have an image later on that kind of illustrates what happens when you do that. And then we talked about path tracing, bidirectional path tracing, where you can say, well, you could shoot them technically from both places, from light sources and from cameras, and then just connect them. All right. So the idea here, one of the first things you have to solve when you're writing a ray tracer is, okay, where are my camera rays going? All right. So one of the first problems to solve is I have some opening on my camera, theta, and I'd like to shoot rays through the center of each pixel. Or if you're doing more advanced ray tracing, you might want to send more than one sample per pixel. So we looked at the complete angler, which was Turner Whitted's paper, an improved illumination model for shaded display. And this kind of classic computer image kind of demonstrated that you could solve three of the big problems that was happening in rasterization, which was shadows, reflections, and refraction. So those were three problems that they had independent solutions, but none of them were working together. And even when you do rasterization today, it feels like you're piecemealing things together to work correctly, okay? So, shadows, we solve that problem by shooting shadow rays. Reflections, we just, use our reflection formula. We reflect across the normal. And then refraction is, you can use Fresnel to kind of determine how much of this, what is the direction of the ray that, as it travels through a different medium. But the problem here is that you get exponential growth per pixel when you do this classic Whitted style ray tracing, where if you're shooting reflection, refraction, and shadow rays every single time you go through each pixel, and those in turn have to look through every object just to make sure this is not this is not a sustainable algorithm. This is going to be, you're in algorithms class, this is the opposite of what you think a good algorithm looks like, and yet this is exactly what Whitted proposed. But on the other hand, it solved the problem, right? So given the constraints, it solved the problem. Now, improvements came in the 80s for ray tracing, and some of the big ones are in the 90s, especially as path tracing was getting more use in the film industry. But Kajia in 1986 basically decided, we have this rendering equation we learned about, and he also brought along with it a lot of different Monte Carlo methods, which had previously been used in the physics community for simulating atomic interactions with each other, right? We talked about the nuclear bomb, the Manhattan Project, and how Los Alamos National Labs are using this technique, Monte Carlo, named after the famous Monte Carlo, named after the famous Gambling. Yeah, the gambling city in Europe. All right, so try random methods. And so there's a lot of math showing that statistical integration can be very effective at getting you answers, even if you can't do a continuous integral. All right. We looked at, we talked about Cook and others, right? Distributed ray tracing. And so the idea here is that you can distribute rays over time and space. So in other words, instead of just sending like a ray straight through the middle of a pixel, why don't you sample the pixel in several different areas? Or what if you sampled the reflection of the surface in several different directions? So you can get glossy reflections as opposed to mirror-like reflections, right? So this is a game changer for things like metals that, you know, don't look, not everything is a mirror, okay? So this kind of helps with the, with the mirror thing. Helps with translucency, right? Because you can have colored shadows, but you can also have some materials that actually have holes in them, and you get different, you don't get colored shadows, you get gray shadows from those. Motion blur, so you can actually move the object in time, right? So if we look back at this image over here, this is exactly what's going on over here. So this is the only difference between this and the original Whitted one, is Whitted didn't have motion blur, all right? But if you sample the rays in time, then you can get things like motion blur because you're sampling where the object is supposed to be. And then you can get anti-aliasing by doing subpixel measurements, right? Gloss penumbra has to do with shadows. So instead of just shooting one shadow ray, you can send shadow rays in several different directions. So you can adequately sample area lights, and area lights are going to be the main cause of soft shadows inside of a 3D scene. Okay, so distributed ray tracing. And then in the 90s, we got some better methods or more robust methods for actually doing path tracing in real time, which we looked at last time. This is an image, classic image generated. Well, this is a recreation of the image, but this was the distributed ray tracing. This was like the poster child of like, here's what we can do with ray tracing now, right? So this is kind of what you could do with ray tracing before, and this is kind of, here's what we can do with ray tracing now. And you see we got motion blur, depth of field, the reflections don't necessarily have, well, these ones are kind of perfect, but if you had a metal surface, you know, you could model that. All right. We looked at Disney's practical guide to path tracing, and this is a screenshot from a shader toy that does path tracing. So, you know, one of the things, if you're getting real-time results, you typically are getting a couple samples per pixel, and then that's it. All right. So if you want to, you typically have to do some kind of denoising. That's kind of the work going on today. But they kind of explain some of the practical aspects of how do you actually do it. Like, you know, you had to batch rays together so that you can kind of get some efficiencies on the computer, right? And process those in parallel. So one of the approaches that kind of increases the speed of path tracing is bidirectional path tracing. So we mentioned you could shoot rays from the lights into the scene, and you can shoot rays from the camera into the scene, and then you just connect it. So after some depth, you decide, okay, let's connect all these samples that I put my lights at, or all the rays that they ended up at, and connect them with the rays that I got from my camera, okay? And then you can use the BRDF to say how much of this reflected ray here actually gets to this side. So that's how you connect the two. Use the BRDF, and the BRDF will tell you exactly how much light is reflected in this direction from this surface, and this BRDF will tell you how much light is then reflected back. So a nice, easy way of connecting those two. And each kind of shows some of the implications there, right? Bidirectional path tracing with 25 samples, standard path tracing with 56, and the same computation time. So this result is far better than this result. And you get, so having this kind of improvement, I guess, you know, as far as time goes, is pretty massive compared to what you had to do before, is just wait for the samples to converge. All right, and then we looked at Metropolis path tracing. So the idea here is that you would just move these paths around a little bit, depending on where you're getting the better results. and you can get some, so this is also a same time frame kind of deal. So given bidirectional path tracing, by using mutation, you can get better results for certain kinds of characteristics. If you look closely though, you'll notice that bidirectional path tracing has much better convergence in like the edges over here, underneath the table. You can tell this is a significantly noisier image. However, compared to this one, however, this when you compare the caustics associated with it, the Metropolis is going to give better results because it's able to spend more time adjusting all the rays in that localized region. All right. So it's not good as a general algorithm, and it can be very tricky to get working, but for particular kinds of effects, it can be very useful. So I would expect if you're working on an advanced ray tracer, then you might spend time determining, well, when should I use Metropolis and when should I just not use it at all? All right. So this makes Metropolis, I just illustrated because it's a more sophisticated algorithm, but it does have its problems. We talked about importance sampling. In other words, regular importance sampling where you have like one function, you can do something like Fresnel reflection. We know that when you're incident on a surface, you get, and for a dielectric, you get the least amount of reflectance. In other words, most light's transported, through the medium. So if I look straight down into a pool of water, I'm going to see straight through the water with very little reflection. But if I'm standing at the edge of the pool and I'm looking towards the other side, then I'm going to see the most reflection. Okay. So if you use the Fresnel to trigger when you should reflect and when you should refract, then you can use that. That's called importance sampling. You can cause that to choose the ray that's most likely to make a difference. So you're always choosing some rays that you're likely to get less information from. So that makes it still what we call unbiased, but you end up spending more time tracing rays that contribute to the final image. Okay. So what Veach was trying to say is that, well, there are some problems though, because if you try to sample the light source, in other words, you try to pick directions that are more biased towards the light source, then there are some instances, like if the shininess goes up like a mirror image, that you tend to have really bad results for that. However, if the other important sampling approach is to use the BRDF, then on glossy surfaces, it tends to do worse. So he used to introduce the idea of multiple importance sampling, where you can combine, you basically randomly pick between sampling the light source and sampling the BRDF in a way that makes sense, so that the path tracer can still be unbiased. In other words, when it's finished, you get the same result as if you had just not done these optimizations. But he shows that you get better results with glossy surfaces and reflective surfaces. So this is a great way of getting more bang for your buck for your path tracer, is by using several different functions. All right. So, right, we see regular path tracing, bidirectional path tracing, adding Metropolis, multiple importance scanner. These are all like important things that you would do in a path tracer to get the best images for the least amount of time. Okay. You can still write a unbiased path tracer that gets the same results. Just remember, it'll take longer. More samples have to be collected in order to get the same results. So other approaches include radiosity, virtual point lights, light mapping. Some of these rely on us understanding the radiosity equation. So in other words, we talked about our scene being divided. We have our geometry. We might divide it into smaller subpatches, and we're interested in how much light is reflected from each patch to each other patch. All right. And so this is basically, we're simulating thermal, it comes from thermal heat transfer. So ironically, if you want to get some more graphics information, get yourself a book on heat transfer, which I did a few years ago. And I was actually surprised that I got more information about the Fresnel function than I ever did from any computer graphics book, because I guess they do a lot of Fresnel type stuff with the heat transfer, because you're dealing with metals and so on. So I was looking for metal information. Remember, I showed you the demo with the metal reflection. So ironically, heat transfer is a good subject area if you're trying to find more information on light reflectance and so on. Okay. Let's see here. Okay, so we have radiosity. And so, like I said, the idea is how much, under this hemisphere, how much of this area of patch, so we can project an external patch or a form factor onto this hemisphere, and we want to find out how much of this light will then affect the area that we're integrating over. Okay, so this is our big omega. That's the hemisphere that we're looking at. So Cohen and Greenberg, in advancing the radiosity, came up with this hemicube method, where you could, instead of having a hemisphere, you have a hemicube, and so it would be easier to figure out how much light then is transferred from one patch to another by sampling the hemicube. All right. So I grabbed this image here just to kind of show you that this is one approach that you could try. And so the main idea here is that, you know, if you have direct illumination, we kind of know which surfaces get the light initially, and we'd like to find out how then that light reflects around the environment. All right. So this is a multi-pass algorithm. In other words, the first time around, you can't expect surfaces that are not visible to the light to get any kind of light. And so you have to do several passes before you can call it good. So after about 3 passes, you get most of the light. However, there's still dark areas that would need to kind of settle over time. Okay. This is a good, well, I don't know if I can do that right now. There's I'll show you this on Wednesday. There's a cool video where they would shoot light pulses, and this is at MIT or one of these other big school universities, and they were shooting light pulses into this bottle and measuring the time that they fired the photons at, and they're able to kind of trace a single photon as it traveled through this Coke bottle. And it's actually a pretty cool video. So I'm going to find that. So you can kind of see that it actually kind of works like this in real life. You know, those photons take time to kind of bounce around before they get to your eyeball. So we took a look at this scene over here. And so, you know, the way that the radiosity would work, you know, here's our raw material colors, and here's our raw geometry. And so in order for us to even process the scene with radiosity, we need to divide it into smaller areas. So we go ahead and subdivide this, and now we can render, or we can calculate the radiosity from each patch. All right. So in order to do that, after we've done it for a while, you'll notice we get this very raw looking image, right? This is not what we think of over here. Okay, so we got to do some filtering first off. And once we've kind of done the filtering from the neighboring patches, then you can see that it's looking pretty good. All right, our limitation is primarily the amount of resolution that we gave to each patch. Right, so if you notice, the problem areas are the patches behind the behind this cabinet. Right, so back here you notice they're really dark, and that's because you don't have very much light reflected on that entire patch. So that's a problem. But if we filter it out, then we can kind of smooth out the results a little bit. And we can kind of see what happens after each iteration. So after the first iteration, you'll notice that we get, you know, the base reflectance is kind of everywhere. We kind of spread the light everywhere. After 2 iterations, we're kind of bringing up the energy level, right? Lights kind of bounce some more. After 3 iterations, and then after 79. Okay, so you can tell there's significant energy loss between the 3rd iteration and the 79th iteration. So one common technique is just, if you can kind of estimate what the ultimate brightness is going to be for the room, you can just offset it. So you can kind of bias the result up so that it looks almost the same. All right, because the main difference is just total intensity, okay? So we mentioned that the patches were a problem. So one of the ways to do that is then to subdivide each of the smaller patches. And by doing that, we can figure out what are the areas that are giving us the most problem. So what do you think a good mathematical tool would be to determine whether we should subdivide a patch or not? Gradient. Yes, great answer. Gradient. So if we have a large gradient, that means we should probably divide this one up some more. And if there's not a very big gradient, then generally there's not a lot of variance there. So we don't need to subdivide in that area. So typically the areas that are shadowed most, you'll see we have a lot more samples over here, and this will help our shadows get smoother. And over these larger patches here, those are darker. there's not much variance in the shadow. Okay, so that's one method we can do to improve the quality of radiosity, is to do adaptive subdivision. All right, one of the areas where radiosity is most used is light mapping. So we basically pre-calculate the lighting inside of an environment, and then we just store those in a texture map. And then when we render at, the main result is that you basically get radiosity for free. Okay, so this is a very common technique. Unreal, Unity still use light mapping, and they also use another technique called irradiance volumes. All right, so irradiance volumes are, the other technique is called pre-computed radiance transfer. And the idea here is that, and just so you know what a radiance is, if you can think of radiance as the amount of light traveling through area, okay? Irradiance is the total amount of light then that is coming in at a surface, all right? So if you imagine radiance is what's getting reflected, irradiance is everything coming in at a certain point. That is basically that hemisphere of illumination, okay? So what we'll do is we'll use spherical harmonics to represent this irradiance because it's a form of compression. And what we can do is take a high frequency function and turn it to a low frequency. In other words, we typically want to do things like glossy reflections, or we'd like to just see what an object looks like inside of its environment. So we don't want something that's like high resolution and lots of detail. So in order for us then to use this irradiance, we have to kind of figure out, well, for the model, how much of a vertex is actually going to be, can even be reflected, okay, at that point. So if I was looking at the teapot model, I would expect that underneath the handle, where the handle connects to the teapot, that I would probably have less probability of getting light in that area than I would on the outside surface, okay? So after we've computed these spherical harmonics in terms of visibility, like what is the visibility on the hemisphere for any point, then what we can do is then at render time, we just combine this irradiance with the visibility function, and we can basically separate the lighting out. So we can pre-compute the lighting, and then in real time, we can compute the lighting value for that model using the pre-calculated visibility spherical harmonics. So I first learned about this stuff a few years ago. Robin Green wrote this really good paper called Spherical Harmonic Lighting, the gritty details. Really good read if you're interested in how these work. And this was kind of started out by work by Peter Pike Sloan for Microsoft. And him and his research team really kind of showed why this is like amazing. What was kind of neat is Robin Green, he was a researcher working at Sony. And so Peter Pike Sloan actually emailed him a preprint of the paper that he was working on. And so he said, yeah, because he submitted it to SIGGRAPH. And so he was, Robin Green basically told his manager, you know, I bet I could have this implemented before SIGGRAPH starts on the PlayStation 2. And so what he did was, yeah, he actually, you know, he spent his time like getting this algorithm working on the PlayStation 2. And so this is I think why one of his he kind of has like a good, here's what it's like from the trenches, and then Peter Pike Sloan is kind of giving you the theoretical framework for this. Okay, so here is from this paper right here, fast arbitrary BRDF shading for low frequency lighting using spherical harmonics. So in this and this is what I think is kind of like the killer app for pre-computed radiance transfer. We have a brushed metal head model, and this is used in it's the exact same reflection model, but it's used in a different environment. And so what do you guys notice from these four models? The color impact, okay. What else? Light direction. Yeah, this one I think is really apparent, right? You can tell the light is coming from the side versus, you know, an arbitrary place. What else? Even more basic than that. Let's look really basic. What would happen if you were to take this model and stick it in this scene? Would it look right? Would you believe it? Would it be believable? No, it doesn't look like it belongs. But when you put this, when you use the radiance volumes, then they look like they belong. Anybody seen one of the original Star Wars movies with the George Lucas enhancements? One of the things I notice big time is when they add a 3D model, sometimes it feels like the model doesn't belong in the scene. Like the lighting is just a little bit off, and I'm like, I know they plastered this over the original film, and they probably tried hard to make it look like it belonged, but sometimes the reflection is just a little bit weird. Like it doesn't look quite right. And in fact, everybody's seen Avatar? Are you familiar with Avatar? So Avatar is one of the movies that kind of started using these spherical harmonics kind of for the first time. And what you'll notice as you go back and watch movies starting in the 90s and early 2000s, is you'll notice that when they did computer graphics, that it feels a little artificial. It felt great at the time, right? But they look a little artificial because the lighting is kind of like, it looks a little weird. And as you watch movies that have been done in the last decade or so, when they're using these irradiance volumes and path tracing everything, that suddenly the objects that they stick inside the scene feel like they belong in there. They don't feel like they've just been rotoscoped in on the movie frame. Okay, so pay attention to that. Watch an older movie and be like, oh yeah, that doesn't look like it belongs in there. It looks like they rendered it and they added it. But you look at later movies when they can actually afford to like take the video. They can take measurements of the environment that they filmed the actors in, or they can recolor the film so that the actors inside the green screen actually look like they belong inside the scene. So there's some things that you can do there. All right. But the biggest thing I feel like it makes the models look like they belong in those environments, whereas before, not so much. So here's the classic way of doing ambient lighting in computer graphics is like, what do you think the easiest approach to doing ambient lighting in classic computer graphics is? Simplest approach. What do you think is the simplest approach to doing ambient lighting? Like, given the choice of, well, ambient lighting is, you have your illumination, like say from a point light, and it's shining. So objects on the other side of light, right, or in shadow, are going to be black, pitch black, and then you have the shading on the light side.
Render the light as a camera view, project that onto the geometry, and then blur it.
Well, that is something you could do, but it's not the easiest thing you could do. Easiest, like one pass. What could we do to instantly like make sure that our dark areas aren't like pitch black? How about just add a constant value to it? So if it's black, instead of having values go from 0 to 1, just have them go from like say 0.2 to 1. Right? Okay. I mean, kind of, if you look here, that's exactly what we're doing over here. So, you notice that this isn't black, it's kind of like a really dark gray. Okay. So as we kind of manipulate this, we can, it doesn't look like it's completely like, it's very rare that you ever walk in a room and you shine nothing. I guess I might call it the Doom 3 effect. How many people have played Doom 3? Man, this is before your time, I guess. So one of the things about, I'll just pull up an image of Doom 3, just take a look, because Doom 3 is kind of known for being dark, right? One of the big things about Doom 3 is like, this is not realistic, right? If you are inside of any kind of environment, it never goes to black. Like, I've never been in an environment where there's this much lighting on the wall and this much shadow on the wall. It's never going to happen. Okay, the light is going to bounce around. And so because this just doesn't look realistic, I mean, it makes sense for like a horror game, I guess, if you want the shadows to be dark. But it doesn't look very realistic. So over here, though, if you compare this with the radiance volumes, this is using pre-computed radiance transfer, you notice that all of a sudden that, yeah, the areas in the corners should be darker, right? Because not as much light's going to get in the corners. It almost looks like ambient occlusion, but this is a slightly different method. You can kind of do ambient occlusion using some related techniques, but you'll see over here that, you know, given this scene and this scene, you would probably sell more games with this one. Okay, just because it looks better, it looks more realistic. So how do we do that? So I mentioned earlier using spherical harmonics. And if you know anything about Fourier series, then you know that you can take a complicated one-dimensional function and you can approximate it with a bunch of sine functions, all right? How many people have never seen Fourier series before? Or you've only heard it, but you don't know what it does? All right, that's okay, because I mean, truth be honest, Fourier series is not like something that, it's a word that gets thrown around and probably fewer people understand what's happening. Okay, but as soon as I show you what a Fourier series is, yeah, that's probably a good one right here. So the idea here is that you could approximate, say, a square wave with a single sine wave, right? Although it's not 100% accurate, but as you add successive sine waves on top of it, like that double in frequency, then and you add them together, then you'll notice that we can approximate the sine wave, or you can use sine waves to approximate a more complicated function. Okay. Let's see here. This is some of the reason why Fourier series is, like, most people don't understand it, because you stop at Calc 3 and then you stop learning about math, and they don't talk about Fourier series in that kind of a course. Here's another example. So you take a couple of different sine waves and you add them together, you get a more complicated function. So the more of these that you add together, you can figure out some constant value that you can multiply on the amplitude of each of these sine waves, that such that when you add them together, then they will approximate your function. This might be another example. Lots of different sine waves. Okay, but we'll see what happens with spherical harmonics. These are the same idea, except that it's on a sphere. All right. So if you think about, you know, we've been talking about the hemisphere representing irradiance, so amount of light coming in from each direction. Well, let's just say that instead of it being like a flat surface, like on the table, let's just say that we put that in space somewhere, like this point over here. And I'm going to measure a light probe around this area. All right. So what we actually have here is a spherical function for this single point in space. We have a spherical function. So in this particular room, because that bright light's coming from over here, we might have, you know, strong light coming in this way, and maybe a little bit of reflected backlight coming in from here from the slide projector, and maybe very little light coming from the ceiling and the floor. All right, so you can think that directionally there is a component that we'd like to, I guess, model, right? So the idea here is that if you assign a scalar value to each one of these functions and then add them together, you can approximate some other more complicated function. For example, if here's my three original functions, okay? If I were to take just the first, and we'll call this a band, the first band, you notice it's just a sphere, right? So if we only use a sphere to model each one of these, clearly we're approximating it with a sphere, but it doesn't represent what the function looks like. If we start to go to n equals 2, in other words, if we pick this band, these bands, and this band, okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 spherical harmonics, then we can take each of these models, and this is what an approximation would look like using spherical harmonics. If we go all the way to 10, all right, if we go all the way to 10, and basically what's happening with these is you just get more lobes. They start repeating more frequently. You can see that as we add a scalar value for each one of these and add them together, that now we're getting close to approximating what it looked like before. And so this is what I mean when I say high frequency and low frequency. So low frequency means we don't have as much detail, but we are representing kind of the idea behind it, all right? This is very handy for like glossy reflections because when you look at a glossy surface like the tables, right? They're glossy surfaces. I can see the reflection from the back screen on the tables, but I can't make out what's on the screen. All right. I can see some hot and dark edges. All right. And so this is nice though, because then you can do model glossy reflections. All right. So here is another picture that Robin Green took while he was doing his work here. And so this couch was one of the first things that they modeled. So this is point light shading. This is what you would typically use in computer graphics. You have a light somewhere in the scene and it's just shining illumination, right? So what happens is that I can kind of tell that the light is coming from, I don't know, this direction, right? It's coming up and to the right. And because of that, we see that the sides of the couch is black. There's no illumination there, right? Just kind of like Doom 3 illumination where it's no view of light, so we're going to call it black, okay? And if you were to flip the light all the way almost on the side, we see, because cosine, right, the cosine of n dot L, so the floor is pointing up. As the light's coming down, the cosine between is getting very, very close to 0 as the light comes down. So over here, I guess actually the light's coming from straight on this direction, all right? But we have very little reflection. So this is not realistic at all, because we know that if this was actually illuminating this room, that we would get some bounce off of the couch onto the floor and so on. All right, so with spherical harmonic shading, on the other hand, we can see that we can approximate those secondary or third bounces from this scene geometry and convolve it with the irradiance volume, right? So we can, for each one of these, and I don't know if I have the image there or not. I don't. Let me show you this image, spherical harmonics. There's an image of a teapot that I'm looking for, and I meant to copy that and put that over here. Maybe it's on this page. They have a demo, but I didn't download it. I'd have to compile it. I'm gonna see if they have. Nope, that's not it. Maybe it's smart enough to know I'm looking for a teapot. There's the spherical harmonics with wedded digital. Yeah, they're the other. So we were talking Reyes architecture, and so Reyes architecture is what they were using for a lot of the earlier movies. All right, so Lord of the Rings and so on. Path tracing is still kind of new because path tracing is still very expensive. So everything that, a lot of the research, the advances in research for the for games and stuff have come from movies because they're trying to push the edges of realism. It's nice to see a lot more images of spherical harmonics coming out. Where is the one with the teapot? This is a good case. If you find it, you should definitely save it. Okay. And I had a demo at one time that actually showed you the spherical harmonics, but basically you calculate a spherical harmonic, not just for the rate, like the actual surrounding environment, but you also record a spherical harmonic for each vertex as well that says, okay, how much light is visible. So I'll give you for an example. if you were calculating a spherical harmonic for this side of this page, right? Then you would say, is this visible? Yes. Is this visible? Yes. Is this visible? Yes. Is this visible? No. So your spherical harmonic would be kind of one-sided, right? And if I put like my hand here, then we'd actually see a lobe coming out over here and a lobe coming out over here because I'm blocking it. All right. So the spherical harmonic will basically tell you how much of this spherical harmonic is even visible. And you just multiply. The cool thing about it is you just multiply the constants you have for the spherical harmonic lighting and the one that you have for the surface. And that's what allows you to do multiple reflections kind of built in. So this is an example of what they look like. So this is using some of my research using, I was rendering spherical harmonics. And so this is a path trace view of what the light probe would look like. And this is a spherical harmonics reconstruction of that same scene. So you can see high frequency, low frequency, all right? And we see that if I were to look at a 3D model of the spherical harmonic, you know, just for perspective, this is like, it's a building with one side that's been removed. So the sunlight's coming in one side of the building. So we have this huge lobe over here that represents all the incoming illumination for the scene. And of course we get some backscatter as well, all right? And so this is what a 10-degree spherical harmonic looks like for this particular scene. And this is what the image would look like if it was a cube map. All right. So, so how detailed do these have to be? So you can use path trace. This is how you typically make these irradiance volumes, is with path tracing, because then you can actually feel out where all the light is. But you don't need a whole lot of samples in order to do that. So for this one, this is an example of what path tracing looks like when you take just a few samples per pixel. You get a lot of dark areas, but if I were to sample this for spherical harmonics, you can tell that I can reconstruct a smooth image that I can then use that doesn't have the same problems anymore, but more or less reflects the environment. So in this case, I can see the green here is due to this 3D model that's kind of a cyan color. And then we get some magenta from this other object that has a magenta color. So let's see how we use this. So typically what we do with the radiance volumes is we record several samples inside our 3D scene, all right? So this is a walled off room. This is some object that we'd like to render inside of it. And so these are all different spherical harmonics recorded. And now we'd like to make it usable. So in order to make it usable, we can interpolate one spherical harmonic to the next. So what we'll do is, say over here, I think these are numbered, all right? So this is 1, 2, 3, 4, 5, 6. So if I had an object that I wanted to render inside of here, I could take 1, 2, and 4, and I could interpolate the constants together. So I could blend it like it's a texture map, right? So we saw like trilinear texture mapping will take several texels from nearby things and then find out what it ought to be, right, given that location. So what I'm going to do here is you can do a Delaunay triangulation with these lights, and basically now no matter where you are, you can isolate just 3 of these spherical harmonic lights to light, right? You don't have to worry about, well, do I need to include this one or this one or this one? You can always triangulate a tetrahedron, which is 4 sides. So this is 3 dimensions. So a triangle is the simplest one. But in a 3D graphics engine like Unity or Unreal that's using pre-computed radiance transfer, they're going to create a Delaunay triangulation for the entire scene, and that's going to create these tetrahedrons. So these 4-sided, 4 vertex points. So then we have 3 let's say we have 3 points we're interested in taking a look at. So we'll take this first one, and what we do is we identify that these 3 irradiance volumes will contribute to this vertex. So then we'll blend them together, and then we'll calculate what the irradiance should be at that particular point in space. Okay, and we'll do those for the other 2 values as well. You'll see that at this, if we chose a different point, such like this space, then we use another set of irradiance volumes. Okay, so what's nice about this is that if you have a character moving through a static environment, then you can use pre-computed radiance transfer to say, here's approximately what the global illumination is going to look like around that character at that particular time. And you can do it dynamically, right? So one approach to this is that was really popular in the early 2000s was computing an irradiance volume that you can change, all right? Because there's a problem. As soon as you get further and further away from the irradiance volume, you're probably getting errors. Like if I stuck my object right in the middle of where one irradiance volume was, that should be accurate. But as the sooner or the further away you get away from there, you're kind of extrapolating data. So you don't know for sure that that's what it's going to be, but you're kind of, you're closer the more samples you take, okay? So let me find, I have a demo that I can show you called Dangerous Curves. And this was from 2004 using DirectX 9.
So on that example that you were showing where the radiance volumes, some were lying within or effectively your shadow areas within the vehicle area, would you, or do you know of any demonstrations that did the distribution when it tried to increase sampling in areas like that?
Kind of. I can kind of show you a little bit what's going on with this demo, because it's kind of doing something. So one thing you can't see in this demo is they have a track of irradiance probes going along the inside of the tunnel. And so they can use those, they can switch from probe to probe, kind of affecting the reflection, okay, of the different environments. So if they were doing, say, just regular diffuse global illumination, in other words, they can more or less say, this is approximately, I think this uses like ambient occlusion. This will basically tell you which areas are more likely to be lit by the surrounding environment, right? When you add the irradiance volumes, all right, then what it'll do is then if the environment changes, so let me switch over here. If the environment changes and it tends to be more like the colors are changing, so you're in like a blue area or a reddish area, those will have an effect. So if I were to like hit escape on this, oops, if I move it around, it'll get thrown off. Okay, so you'll notice that as the environment's changing, if I were to switch back to just regular, there isn't a whole lot of variation on the color. And if I add it on, then you'll see that the surrounding environment has a chance to change the illumination on the 3D model. And you can take advantage of color bleeding. Let me quit this. ATI, I'm going to find the presentation. They gave a presentation at GDC in 2005, right, for this particular, and they talk about a lot of these things. So here's a radiance volume, Gregor 98. This is kind of one of the first work where they would just put all these volumes in space kind of on a uniform grid. And then what you can do is, so they're just explaining how the irradiance works. There's Fourier theory where you add several sine functions together, you get your complicated function back out. This is kind of talking about why you need to use irradiance gradients, okay? So this is the lighting, and the center one is basically ground truth, okay? So it's clear over here that, yeah, this side of the sphere should be red and this other side should be green, okay? Now, the problem is as you move further and further away, you're still using the same irradiance volume. And so it still looks like on this side that, that your green is coming from the right and your red is coming from the left. Whereas this is ground truth over here, where it shows you this is what your object should look like if it was actually in the scene at this location. So this is an approximation. It's better than just a solid ambient color, but it's not entirely accurate. So what you can do is you can use an irradiance gradient. In other words, you can say, how is my light changing as I work my way left to right? So if we start off here and have one gradient and we're basically interpolating between the next one, then we can just blend them together smoothly going from one area to the other. And so this kind of answers your question, you know, how can you kind of get around that? So obviously the more samples you take, the more accurate it's going to be, because you'll notice over here, like in the center, that it's not quite as dark in the middle as it is over here. So there is some approximation issues going on, but clearly this is more, it's a lot closer to the ground truth than the other the other approach.
So they're taking they know the irradiance of each individual sphere based on the sources of light that has come from.
Yes.
Rendering each of those. Are they just doing the spherical harmonics for data compression purposes, or why wouldn't you just keep the full?
The reason you do
data?
The reason you do the spherical harmonics is that if you basically have to represent the cube map for every single one of them. So if you have like a 128 by 128 by 128 cube map, or you know, times 6, 128 by 128 times 6. Whereas if you use a low resolution spherical harmonic, which has got 9 coefficients, right? Then that's 36 coefficients for red, green, and blue. That's way cheaper to send to your vert. You can do this per vertex, and each vertex could probably be processing its own set of irradiance values. All right, so it's very cheap to send it per vertex. Okay. Oh, there it is. Okay, so over here, you know, this area is in shadow, but the idea here behind pre-computed radiance transfer, right? You can calculate a visibility spherical harmonic, and then you can just multiply this spherical harmonic with the surrounding environment. So clearly, anything coming in these angles where those two lobes are will be reflected, and everything else, like on the other side, would be black. So they wouldn't. So that's how you get around. You know, wait a minute, you're recording the light over here, you know, but the light. This is the only side you'd be able to see the light. So by just multiplying the coefficients together, ironically, or you know, incidentally, you happen to ignore the light coming from here because the visibility takes into account that you can't see that. All right, and however, because we can simulate, we can do path tracing, I guess, to figure out what this spherical harmonic should look like. You can figure out, well, what about those secondary and third bounces that might reflect off the backhand of the teapot and then out towards the other side of the scene. So you can still include a little bit of that because you get that back reflection. Okay, rotation, that's a little more complicated, but the idea here is that you know, if you were to rotate the model, then you have to rotate the spherical harmonics, and that's not exactly a cheap thing to do. So you normally just kind of cheat and rotate the spherical harmonics instead of the model. So there's a way to do that inverse transform. And that's here. So there's the radiance volume. Ignore that. They're talking about octrees in 2005, but later on they're going to use Delaunay triangulations. So we're going to ignore that. So they're talking about the interpolation, right? So in this case, they can interpolate between the two. So if you had these spherical harmonics, when you interpolate, this is what the result that you get. So this is basically, if you look at this tricubic interpolation, these are all the irradiance volumes. This is the one you're trying to calculate. You're trying to create a new one because you got to do that per vertex because the vertices are going to be at different spots inside this 3D space. Okay, this is where they kind of give you an idea of how much memory this takes. So they tell you can store what 1,000 to 2048 floats in your constants, although it's larger today, but you got to think 2005, that's still mobile technology-ish kind of today. So you can't just throw a ton of stuff inside your shader, but you're looking at, for a 6-order spherical harmonic, you need at least 432 floats per sample. All right, so that's how big your vertex structure has got to be at least. Okay, now here's what they do over here. So in the actual demo, they basically have a bunch of irradiance volumes that they have put on the track. So they pre-compute this using the actual 3D model of the scene. Okay, so they ignore the fact that they're going to put models inside of the scene. So yes, it would be more correct to say if you have a giant 3D model in the middle, it's going to affect your radiance volume. But for games, they just say, well, let's just ignore that for now. Okay, and we'll just calculate these irradiance volumes. Then what they can do is they can create the gradient just by saying, okay, now the model's over here, so use this set of spherical harmonics and then blend the two. So they can kind of get an idea of where the lighting is probably going to be. All right, let's see if they had any backup slides. Okay. And if you're looking for light probes, Paul Debevec has done, he's kind of the guy who introduced high dynamic range stuff to computer graphics. That's kind of his bread and butter there. And so that's what a lot of his research was doing. So he actually has light probe galleries. This was in 1999. And so there's a couple of radiance probes that you can use. And you'll notice that these have been used frequently. In fact, these are on Shader Toy. Some of these are on Shader Toy. Okay, so if you want to kind of simulate this environment, then there's a skull lit up with that particular environment and so on. Okay, so there's some, and then these are the HDR images are basically the high dynamic range, or you can pick, I guess, TIFF, which is 8 bits. Anyways, the idea here is that you can illuminate synthetic objects with real light. So this is about making those images look better. All right, so anyways, pre-computed range transfer, we want to render the points here, and we're going to blend these surrounding lights or irradiance volumes together. So we can calculate this interpolation between the 4 different irradiance volumes. Okay, so as I mentioned, this is how they basically do it. So for example, this is you can either put these in place normally in your 3D engine. So in Unity, they have a way of basically, you can say, here's where I want all my spherical harmonic lights to be, or not, they're not lights, but they're volumes. And then if there's a 3D model in the middle, it'll light those up with these this mesh here. Okay, so here's another example of putting this light mesh in here. So this is how modern games are done. You know, you have an artist in there either manually placing these lights or having a tool automatically place all these irradiance volumes. Then they have to pre-render the irradiance volumes, and then they ship those with the game. And then every dynamic object moving around will then be lit with these irradiance volumes. And it looks like they're actually going around, right? It looks like you get that global illumination, but without having to compute it with path tracing in real time. Okay, any questions so far? PRT. I think it's a pretty decent technique. And it's, you know, the best thing about it is the math is very simple to do once you kind of get your brain wrapped around it. The problem is you kind of have to get your brain wrapped around the math first. But once you do, then you're like, oh, it's no big deal. Just multiply this set of numbers with this set of numbers and voila, okay? Okay, so going back to real-time ray tracing, we were talking about the 6 components, right? You have ray generation, so this is when we initialize the payload and we shoot off the rays. And then we have the acceleration structure, which is going to test our ray intersections. So hopefully it's using something more sophisticated than a list, right? Because that's ON per pixel. And while it's going through the acceleration structure, it's doing 2 things. The first one is calling the intersection shader if you specified one. And that's like useful for procedural objects. Otherwise, we're say testing triangles, ray triangle intersections. And then if we get a hit, we'll call, if you specified one, we'll call the any hit shader. So this might be useful for saying, you have smoke in the air, so you have some kind of like participating media that you want to simulate. Or I'm shooting a shadow ray, so let's just see if anything hits this in the pipeline, okay? And if it does, and we say it's in shadow, forget about it. After it's gone through the acceleration structure, then we're going to go to the closest hit shader. So if we get a hit, then we'll call the closest hit shader with whatever was the closest object. And this is recursive. In other words, you can call trace ray again and start the whole process again up to some maximum ray depth. So it's not just like a, you know, one hit the first surface and then, you know, so you can do weighted style tracing if you'd like to, or you can do path tracing. And the main difference between the two is that with path tracing, you normally pick one direction to shoot the next ray and average over the entire number of rays sampled per pixel and ray tracing. So let's try to do everything. And you get that, you know, that huge exponential growth there. The other thing they'll do is do barycentric coordinates and a triangle index. So we're going to talk about triangles on Wednesday. So we'll get an idea what barycentric coordinates are, but they're very handy in ray tracing. And then a mist shader is, well, what happens if we didn't hit anything? And this is our way of just saying, well, let's hit the sky, for instance. So some kind of object externally. This is where you would, this is where you'd use your own irradiance volume, perhaps, if you were trying to like model in low frequency lighting. Okay, so this is everything we just say, you know, and the payload is just kind of along for the ride. So we can use that to store things like, here's the normal, here's the texture color, all sorts of things that every shader might need to know about. All right, so that's the book. The different parts that we're gonna, we talked about the mist shader kind of being the simple, we just linear interpolate between either white and blue or orange and blue, depends on what we're trying to do. So that's for the homework. But what I wanted to get in today was, okay, we haven't hit any objects yet. That's kind of the next step. How do we actually do ray tracing? How do we hit the objects? And so there's two approaches. One is you either have an analytic function that you can then solve for, or you can use a numerical approximation. So the first one is if we wanted to ray trace just one sphere in the scene, we have to be able to figure out how does a ray intersect with a sphere. So in order to do this, we need to use the quadratic equation. And you know, as you know, you either get no solutions, one solution, or two solutions. If you get no solutions, then there's no intersection. If you get one solution, then it's a tangential intersection. In other words, both points technically are at the same area on the sphere. And two solutions means you have an entry and exit point. Now, the key to remember here is that our x over here is actually going to be t. We use the terminology t for where are we along the path of the ray. So t will be negative if we're before the start position. So the ray has the origin and the direction. So if t is less than 0, then that means we have gone the other direction. And if t is positive, then that means we're traveling along the path of the ray. So what do you think that the calculation is for us to calculate our current point in space? So if say t equals 1, right, and we have our origin and direction, what is the actual point in space? Well, let's go even simpler. Let's say t equals 0, and our point in space is we have our origin that the ray starts at, and we have the direction the ray is going in. If our t equals 0, in other words, this is the path along the ray, what is the point in space that we're referring to? The origin, right? And so as t gets greater than 0, then we can see we're moving a 3D point in space. We can calculate that point in space. All right. So it's a parametric equation. So over here, we have the equation for a sphere, right? P squared minus R squared equals 0. So if you were to look in a math book, you'd see x squared plus y squared plus z squared equals R squared. That would be the equation for a sphere. Well, we can just say, well, x, y, and z is a point. and r squared is in the radius. So we say p squared minus r squared equals 0. That's that we're looking at the length of the length squared for the point and then the radius. So if that's the case, then we can basically replace p, that's our point in space, with O plus t times d, because we just established that is our point in space that we want to test against. All right. So once we have this, then we can, if we expand out O plus TD squared, then we get O squared plus D squared t squared plus T ODT. So this is just if you had A plus B squared, right? That'd be A squared minus plus 2AB plus B squared. We're just doing our arithmetic. We're just doing our expansion in algebra. All right. So we would get O squared plus D squared T squared plus 2ODT minus R squared. All right. So what we can do is we can map this to quadratic equation because, we have AX squared plus BX plus CX plus CZ minus D equals 0, right? That's our quadratic equation. We have that constant at the end. So in this case, we have A equals D squared, right? There's basically AX squared. There's AT squared. We have B equals 2 times OD, and that's going to be like the dot product. And then we have C equals O squared minus R squared, okay? And so if we plug this into the quadratic equation, we can calculate T. That's what we're looking for is T. So then we have 5 cases. The first case, right, no solutions. We have no intersection. That means that when we evaluate the discriminant, right, the discriminant is b squared minus 4ac. If we evaluate the discriminant and it turns out that this is less than 0, then we know we can't calculate the quadratic equation, okay? If that happens, that means there is no intersection. We have no intersection with the sphere. We might as well just move on from that point. So we check the discriminant. It's less than 0. We move on to the next object. However, if the discriminant is positive, then the next possibility is that you have one solution. And that means that your T0 and your T1, that's your 2 solutions, are the exact same value. That means you have hit the sphere right on the surface. You're just grazing it, okay? And so that gives you one solution. Now, if you happen to hit the ray in 2 spots, so our T0 is greater than 0, or T1 is greater than 0, that means we're in front of the ray. Then our T0 is going to represent, now it doesn't necessarily mean that this is T0 and T1, depending on how you evaluate this. It doesn't, I don't know, well, I don't want to tell you that it's going to guarantee that T1 is greater than T0, okay? But just know that if they're both greater than 0, then you have 2 points on the sphere. So you have to ask yourself the question now, okay, if I'm shooting a ray, do I want intersection 1 or intersection 2? And so what would be the solution for figuring out which intersection that you want? Whichever one is smaller, right? You want the smallest T, because the smallest T moves the ray the shortest amount. That means that you're going to shoot the ray. You're going to shoot the ray of the shortest distance forward. Okay. Now, there is another issue, and that is if you shoot the ray inside of the sphere, okay, you're going to get 2 solutions. However, one of the, because you're basically saying what on this line here, what are the intersection points? So you could get a intersection where T is less than 0 and one where T is greater than 0. So you'd say, well, T0 is behind the ray. I don't care about that one. But T1 is greater than 0. So that's the one I'm actually looking for. Okay. So if you're doing refraction, for instance, and you're inside the glass sphere, then you'd want to see, or you're inside a body of water, then of course you'd want to refract the ray at that point, right? So there are some cases where you're inside the object, all right? So being in a tank of water is one of them. Okay, so it's not like well, why would you ever be inside the sphere? Because we're thinking solids, but there's many reasons you could be in a sphere. Okay, so in this case, you reject the first one and you take the second one because it's the only one that matches. And then lastly, it could be that you get 2 solutions, but they're both less than 0. In other words, when you shot the ray off, they're actually both behind you. And so in that case, you'd say, well, let's skip it. There is no intersection at this point. Okay, so we can see over here, there's 5 cases. This is where all the, you have to basically check, okay, discriminant less than 0, no intersection. T0 less than 0. Don't worry about that intersection. T1 less than 0. Don't worry about that one. We don't have an intersection, so let's just keep going to the next object. All right? That's how you do sphere intersection. Let me just skip forward here. All right, so this is how it works, right? So you hit object number 1, and then you decide whether or not that you should keep going, right? So you have to go through all the other objects. So maybe object number 2 is this cylinder. And so this T is going to be less than this T. So we can say this is now our closest object. And then maybe our third object over here, we test, we see T is greater than our closest one. So the whole time we're doing ray tracing, we're keeping track of what's the closest one that we've actually hit. And that way we can then, it doesn't matter what order that we encounter the objects, we can always figure out which one is closest. All right, so let me go back here. Signed distance functions. Okay, so I mentioned it's kind of hard to find functions like you can do this for a lot of like quadrant type shapes, spheres, cylinders, and so on. But after a while, it does become a little more difficult to actually come up with equations, closed form equations for doing any kind of object. For instance, what if I wanted to take a cylinder and subtract a cube out of it? That's kind of like, what? You know, there's no closed form solution for that. So, or if there is, I don't know about it, or it hasn't been discovered yet. Okay. However, we can do what's called a signed distance function. So if we rewrite the equation, so we start with the equation for a sphere, for instance, and we can rewrite as a signed distance function. So in other words, we solve everything so that the one side is 0 if we're on the surface. Okay. So then if we plug in our points and our radius, then the signed distance function is going to tell us whether we're inside or we're outside. So if our function is less than 0, then we are inside the object. And if our function is greater than 0, we are outside the object. All right. So if you want to think of an example here, you could consider a circle, right? Which if you have a unit circle, then the coordinates for every point on the sphere is going to be x is cosine theta and sine theta. That's by definition. And so if you were to take, if you were to plug in cosine theta and sine theta, let's just assume z is 0. You get cosine squared theta plus sine squared theta. So that's 1. And if your radius is 1, then that's just 1 minus 1 and you get 0, right? So that makes sense. But if somehow we had scaled this down, then our cosine and sine functions are less than, you know, cumulatively cosine squared plus sine squared is going to be less than 1. Then we take, say, you know, say it evaluates to 0.8, like our radius is 0.8 for this point. In other words, we're checking a point that's inside of the circle. Well, then it's clear to say 0.8 minus 1 is going to be minus 0.2. So we get these negative values inside. And if I set the radius, if we set the radius a little bit bigger, like say, or smaller, say the radius was 0.8 and we're looking at all the points on the sphere, then we'll have cosine theta squared plus sine squared theta. So we get 1 minus 0.8. And now we have a value that's bigger than 0, right? So 0.2. And so now we're outside. So we have positive. So we look at the sign of the result, and that's how we get and that's how we figure out whether we're inside or out, by looking at the sign of this signed distance function. So not only is it we get the sign, we also get the distance. So how far are we from this object? Okay. So let's take a look at ray marching. So we're going to take advantage of this by first we set our t to some t minimum value, right? Because we might have several objects and maybe we're keeping track of which closest and which farthest away. And so we're going to iterate, and I'll tell you why we're going to iterate. We're going to start out, you know, if t is minimum, let's just assume it's 0, right? We're starting the ray out fresh. We're going to repeat this process. First of all, we're going to find out what is our point. So the first time around, it's our origin. So because t is 0. Then we calculate the signed distance function. And so we're looking to see if the size of that is some epsilon value. In other words, if we're like really close to the sphere, maybe we're not exactly touching, but we're really close, we'll just say, yeah, we got it. We'll just go from there. We can just stop there and return true. We have intersected our object. If we have not intersected our object, then we can add our sign distance to our t value. All right. So let's just say that we're trying to get closer to a sphere. We're trying to ray trace a sphere. So we're marching along the ray and we calculate the distance. Notice we calculate the distance from basically the end point of our ray. Okay. We have like an end point. So we're just going to march. We have like we know that if we go this distance, then our sign distance function is always going to be positive up to that point. So we can say we can safely move up distance d along the ray without hitting the object. Okay. And then if we hit our, maximum value, like if we jumped outside of our T max value, then we say, well, we're done. So here's a page. We'll maybe look at this page in just a second, but he's written a really good page about lots of different sign distance functions. Okay. I don't know, we'll take a look at it. So let's go over here. This is a guy who has a lot of shader toy examples too, by the way. So this is a great, we over here, like, we have a sphere. So length of P minus S, S is the radius. Well, actually radius squared, I guess. So, oh no, that is just the radius. So we can take the length of P minus S, because length, if you take the length of a vector, it involves a square root, okay? So the sign distance function for a sphere is length of P minus S. So whatever your point is, if you're far out from the object, we're just measuring the distance to see if it's inside the sphere. And then for a box, we can just run this function. So we take the absolute value of our point and subtract the dimensions of the box. And then we can just find out the length for the maximum of Q. So whatever is the maximum value for the max component of Q. And if we add that to all this, basically we can decide if we're in the box or not. How far are we outside the box? So this is using max and min functions are ways of making decisions if you study them out. You can also do a rounded box by this one. It's almost the same thing except minus R. So we can actually use this to figure out, we can make the box round by simply subtracting that radius on the very end. Okay, there's a torus, a capped torus, all these different kinds of shapes that, capsules, rounded cylinder, all these kinds of shapes that would be very difficult to like come up with an analytical solution, right? And that's why in our class, we're not even going to talk about how do you do an analytic solution for a cylinder when you can just use this general approach here for these sign distances, right? Solid angle, rounded cone, octahedrons. There's one of the triangle ones, okay? A quadrilateral. There are some other things that you can manipulate sign distance functions to do, but I'll just give you down at the bottom. Oh, you can do combinations. So if you wanted to, like I said, subtract a shape out of another one, then ironically, you could, if you want to do union, in other words, you combine two shapes together, then you just take the minimum of the sign distance functions. Pretty easy, okay? I can handle minimum. If you want to subtract it, then you take the maximum of minus the first distance and the positive of the second distance. What this has the effect of doing is inverting the shape, right? Because if it returned positive, that means we're inside the shape. And if it returns negative, we're outside the shape. So what we're basically saying is that when we flip the sign on one of these, we're saying, okay, let's make that, if you're inside the shape, we're almost like saying it doesn't exist if you're inside the shape. And so that's why we subtract the sphere, because every time we try to send a ray in there, it gets zapped basically. So in other words, if we're in here and we're adding that T plus equals D, that means if we're inside there, we're actually sending the ray backwards until, we're out of there. Okay. So that's kind of the effect. So if we want to subtract, return the maximum of minus the first one and positive the second one. So subtracting the sphere from the box. And then the last one is called intersection. So only give me where they are both in the same volume. So then we return the maximum of the first sign distance functions. This is so much easier to like comprehend when you're writing a shader than it is to kind of come up with, you know, what's an analytic solution for a sphere or a cylinder, or, you know, for that matter, what is a sphere minus a, you know, rectangle or something. Okay. So then there's some smooth ones. You know, I'm not going to get too much in that, but there you can do some fun stuff with that. We'll probably talk about these rotation ones, scaling, and at a later date. This is an example of a shader toy that uses nothing but sign distance functions for the modeling. I saw eyes grow, like, that's pretty cool. Okay, let's take a look. Hopefully my battery decides it's not going to kill out on us in 10 minutes. Okay.
I'm a little bit confused. So you have these functions that define, what does each of these sign distance functions return? It returns the distance along your ray that it occurs at?
It tells you the maximum distance you can travel. All right. So here's something using sign distance functions. They are very powerful.
Yeah, that's nuts.
That's okay. And these guys, this was actually made by this guy who wrote the other webpage, by the way. He's pretty good. Okay. I'm going to say he's not an amateur, you know, he's been, I mean, that looks pretty fantastic for anything you'd ever see in a game. I think that's pretty nuts. Okay. Let me close that before it like really kills my battery. Anyways, he has a demo here showing all different kinds of shapes that you can do. Now, there are some downsides to them. We'll talk about those at a future time. So going back to the slides, let's take a look at what's happening. So we're going to ray march this ray through this sphere, okay? So the idea here is we calculate, so our T is 0, so we start at the offset of the ray, and we calculate our sign distance to the sphere. So you notice how we go, the ray is off-centered deliberately, because I want to show you what's happening. If our array was pointing straight to the sphere, we would just march straight up to the surface and we'd be done. Okay, but that's not going to happen. We basically find the largest circle that we can, the largest radius of a circle that touches our object, and that is the safe distance to travel. Okay, so if we were to travel this distance, so you kind of see it circumscribed, we're going to get to this point right here. That's going to be our next step. Okay, so then we're going to do our sign distance function again, and you notice we get a smaller circle, right? And this is now our next safest distance to travel. And then it's getting smaller and smaller. So we're looking for our epsilon to be like whatever value. Now, if we miss this, and I didn't prepare an example if we missed the ray, but if we were to miss this, then this circle will then start growing bigger and bigger and bigger. And before you know it, we'd be past our T max. Okay, so this is this numerical integration or technique or derivative technique basically gets us closer and closer to our surface. And then this is why you have to iterate so many times before you can, you know, if you don't do it enough, then you won't converge, and sometimes you'll be missing part of your object. This is something that affected some work that I was doing. And I was like, how come I'm not getting the shape I'm expecting? And it turned out I just wasn't iterating enough. You know, you can't just iterate like 10 steps. You got to iterate like 64 steps, or, you know, so you're doing this like for loop inside of a shader, like, okay, loop up to 64 times where I hit my surface. And it's kind of crazy to think that I'm doing this per pixel when, you know, it wasn't that long ago when pixels were extremely expensive to just, you know, do n.l, you know, that was kind of the thing. Okay, so yeah, another high level thing is that we're basically ray marching towards an object. We're basically saying, okay, what's the largest step that I can get towards it? So as we get closer, that circle shrinks and shrinks and shrinks. All right, so just as a way of comparing, here is a ray intersection with a sphere. And so you'll see over here, we calculate our A, B, and C for our, and then we want to calculate our discriminant, right? B squared minus AC. And so we don't need to do 4. There's a way of like, there's a way of handling that. It doesn't make a difference. But if our discriminant is greater than 0, then we know, hey, we have a solution. And if it's not, then we're just going to return false. Okay. So the first time we check the discriminant and then we calculate, there's our quadratic equation. And if we're inside of Tmin and Tmax, then we can calculate the normal. This is basically what you'll find in Shirley's book, How Do You Do a Sphere, right? We can calculate the normal, and then the P is basically just O plus T times D. So that's the point in space. In this case over here, we have B plus or minus. I wonder if that's wrong. Could be wrong. Anyways, we have the second one. Then we try our minus. Then we need to try our plus. So plus or minus the square root of B squared minus A squared. So over here we subtract. And like I said, looking at this now, I wonder if I was wrong the whole time. But anyways, we calculate the other solution and we check to see if that's closer. So, and then if it is, we return true. We found our intersection. In contrast with ray marching, we're going to start out. So there's our origin, there's our direction, there's our T equals Tmin. And in this case, I put, I think I was debugging something, but say we want to iterate 10 times. So we calculate our point is O plus T times D, and then we check our sphere sign distance function. This radius thing has to do with scaling it up and down, so you can just ignore that for right now. But basically, there's if our D is less than epsilon, then we can just move our point right up to where we calculated the intersection. And then we can call a special sign distance function to calculate the normal at that point. And we'll talk about that more on Wednesday. So we can kind of put all those pieces together. Okay, and then we just increase our, we just march along D if we haven't found the intersection yet. And if we're past our Tmax, then we just say, nope, we're done. Can't find it. Okay, so ray object intersection. And we talked about this. The idea is we check object one. This gives us our new Tmax, right? We're not going to look any further than Tmax. If we do object number 2, then that's below our Tmin because we already found our current T. And so then we can basically stop checking intersections with objects that are just too far away. All right. So this is the general idea of applying the real-time ray tracing then to our whole pipeline. So we're basically going to iterate through the items in the scene graph. So this is different than the ray marching. Ray marching is just how do you find the intersections. Now we want to find out which object do we intersect, okay? So if our scene has several objects, we need to run through this process. So we're going to iterate through the items in the scene graph, and we'll set Tmin to 0 and Tmax to some large value. So that would represent your near clipping plane and far clipping plane. And if a ray intersection occurs, then we can call our any hit shader. It's like, hey, we hit something. And then we can check to see if it's outside our new Tmin and Tmax. So we might have some, we'll mark our new Tmin and Tmax because we'd like to keep track of what our current interval is. If at the end of this, right, we're done iterating, we found an object that we can call our closest hit shader. So this is where we'll do all our expensive lighting calculations. Otherwise, we'll calculate the miss shader. So this is a general way of just doing your basic ray casting. So ray casting is where you basically just give me the closest object and then we'll start shading at a later point. Okay, questions. Sign distance function. What does it mean when the sign distance function is negative? Inside the object. No, right. Inside the object. Yes, negative means inside the object. Okay. What does it mean when your sign distance function returns 0? On the surface of the object. Okay. Let's see here. Who wants to take a stab at irradiance? What is an irradiance volume? What is an irradiance volume? Yeah, getting close. What does it look like? What would an irradiance volume look like? How would you capture an irradiance volume in real life?
360-degree intensity camera?
There you go. Yeah, you could just get your camera, click, 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 and click, and then just stitch it together. That would be, you're just taking a light probe. Like that's how you would do it. Okay. We looked at some, you know, the sphere maps, right? That basically just saying, here's a 3-dimensional, 360-degree panoramic view. That is an irradiance volume. Okay. What was the, what mathematical tool do we use to represent irradiance volumes when we want to do low frequency lighting?
Same one that's using JPEG conversion.
No, well, we didn't talk about those today.
No.
We spent a lot of time talking about this special mathematical tool. Sphere, what is it?
Fourier transform.
That's like a Fourier transform, but on sphere. What are they called?
Oh,
Spherical harmonics, yes. Okay. So spherical harmonics, yeah, that's what they look like, and that they can represent our irradiance volume. And then how do we light an object then with this spherical harmonic? So yeah, you can pick the surrounding ones. That's how you do the interpolation behind them. So I guess take a look at this slide here real quick. This might be a good picture. So at any point, then you can calculate what is all the light coming in, and you can calculate the total amount of light due of reflectance for the environment for every point. And that's because you're multiplying those spherical harmonics, the visibility ones with the environmental ones together, and that basically says, oh, here's your illumination. All right. So what is one of the key reasons why we should use irradiance volumes?
they allow you to move through space better than radiosity model.
Okay, so you can move through space. What's the other one? Appearance, right? We want to make objects look like they belong in the scene that we're, you know, so if we're saying it's in a cathedral, right? It's going to look different than if it's like a afternoon in the middle of a forest, right? That,
But presumably with a static scene, you could achieve the same thing with radiosity, correct?
you can't achieve it in real time with radiosity. You'd have to
Right.
well, you often have to pre-render the environment, right? Irradiance volumes typically are pre-rendered, just snapshot of the environment.
Right, but if you were to put your object in an environment and then radiosity the whole thing, you'd end up with the same result, admittedly a lot more time as.
Right. Well, you'd use path tracing instead. And so, because you know, the problem with radiosity is you have the subdivision thing that you have to do. This makes sense for light maps because you pre-calculate the light maps. It can be high quality. However, if you want to handle your dynamic objects inside of your scene, the light map's no good because you don't have any lighting calculation for them. So hence we would use the irradiance volumes then to store snapshots at different locations in the volume of here's what the light is doing in this area. And then you can light your dynamic objects using this model. And they'll look like they're behaving like they should in that. And it gets us a closer result than if we just used the other approach, right, was just to use a constant ambient value, which doesn't look very good, versus PRT. So this allows you to get color bleeding and everything else that you'd really like to get. Let's see here. If you want some more, like I say, if you want some more reading, then go check out the spherical harmonic lighting, the gritty details. And he talks about, you know, you can get things like color bleeding. So if you notice on the bunny, it looks reddish here. And that's because when you compute the spherical harmonics for the visibility, you can basically say how much light is coming from, you know, even from these multiple bounces. You can add in the extra surrounding colors of light and stuff. So yeah, that's kind of the idea there. So if you want to do realistic lighting in games for dynamic objects, you got to use the radiance volumes. And if you want to do realistic environments, then you typically use light maps for the static. You know, they don't have dynamic things very easily, but and then there's some work of just using spherical harmonics for everything. So even your static geometry is spherical harmonics. So if you want to change the light, then you can just kind of use spherical harmonics then to easily adjust the lighting for everything. So if you have like a sun moon cycle or something, you can then use that dynamically without having to recalculate even the light maps.
You just have different sets of spherical harmonics for different.
Yes.
Okay.
Yeah. So
Okay.
they are very, very cool. Okay. So, and this, like I said, certainly beats just adding a constant value to whatever object you were doing. All right. So let me just stop in the meeting here, but